Hello and welcome to this video in which I provide a gentle introduction to structural equation modeling. My name is Geiser. On this channel I present weekly statistics tutorials related to multivariate statistical methods such as structural equation modeling, factor analysis, multi-level modeling, and latent class analysis. If this is something that interests you, then please subscribe to this channel. Also, don't forget to hit the like button and to check out the description for additional free resources, including a link to my weekly statistics newsletter as well as workshops that I teach for QuantFish. In this video, I will provide an introduction to structural equation modeling with latent variables. And so what is our motivation, or maybe the most important reason for why we would use structural equation modeling? This has to do with the fact that in the social sciences and other fields, we have a measurement error problem, meaning when we take measurements from people or animals, then typically the measurements are not perfectly reliable. So most of the measurements that we take contain error, whether it be test scores, questionnaire scores, physiological measurements, ratings by others, observations, and so on. There will always be some amount of random measurement error associated with the scores from different sources. And so the problem is that this can lead to bias in our statistical estimates when we use statistical methods or models such as correlation analysis, regression analysis, path analysis with observed or manifest test score variables. Then this can lead to bias in the estimation of the correlations. They can be underestimated. Path coefficients could be under or overestimated depending on the complexity and structure of the model. And so then we end up with incorrect statistical results, potentially incorrect conclusions, and also potentially incorrect statistical inference, meaning tests of significance and confidence intervals may also be compromised due to measurement error. And so structural equation modeling introduces latent variables that are corrected for measurement error, and this helps us address the measurement error problem. As we will see shortly, there are so-called measurement models that are part of a structural equation model that allow us to separate true score variance from measurement error variance and to work with the true score variance component in, for example, correlation analysis, path analysis, and regression models, so that we can estimate correlations and regression coefficients at the latent level among variables that are corrected for measurement error. Here's an example of a path analysis with manifest variables. This is a path model taken from health psychology, a model that was proposed by Whitelaw and Young in 1991 for the relationship between physical health and subjective health. And so the idea in this path model here is that there is a mediated effect of physical health on subjective health via functional health, which is characterized here by the A and B paths. In addition, there's also a direct path, C, of physical health on subjective health. So the idea here being that the physical health status of a person directly affects their subjective health, how they rate their own health, but there's also an indirect effect via functional health, because good or bad, we could say, physical health can lead to functional impairment, and that then in turn makes the person unhappy and leads to a lower rating of subjective health. Now, when we estimate the path coefficients in such a path analytic model based on observed scores or manifest variables, then the A, B, and C regression coefficients or path coefficients may be biased due to measurement error, and so would be their standard errors and the tests of significance. And so then this could be a problem if we wanted to find out what is the relationship between physical health, functional health, and subjective health. And so therefore it would be better if we could use variables that are corrected for measurement error, because we have to expect that the scores here do contain error when we, for example, get a rating of someone's subjective health. Then there's almost certainly some measurement error involved in these scores. So let's dive in and let's see how we can make that path analysis between observed variables better by adding latent variables also into the model. And so the way that this works is by means of confirmatory factor analysis. Confirmatory factor analysis is, so say, a tool or one ingredient to structural equation modeling that provides the measurement model or the measurement structure and links our observed variables to so-called latent variables. So for example, we would be interested in measuring a latent variable physical health that is corrected for measurement error. And so in order to do that, we use typically multiple indicators, so not just one score for measuring physical health by some kind of health record, but at least two. So for example, one indicator or observed variable for this latent variable physical health may be the number of sick days in a given year or whatever time period. So for example, we could ask a person to rate or estimate how many days they were sick in the past year, or there might be some medical record available somewhere. And so this could be one indicator of physical health. Obviously, the number of sick days is not a perfectly reliable indicator by itself, because the person may not remember exactly how many days they were sick, and there may be all kinds of measurement errors attached to that score. And so then in order to get more information and get at the reliable variance that is contained in that rating, we would use at least one additional indicator, for example, the number of physician visits in a given year, and there may be a better record of that available, maybe from the doctor's office or something like that. And so then we have another indicator of physical health that's also by itself not perfectly reliable, because not all doctor visits are associated with sickness. So somebody could just go to the doctor for a checkup and not be sick at all, and so then that would be, so to say, there would be some error attached to that indicator as a measure of physical health, because it may not necessarily indicate bad health when you go to the doctor and get yourself checked. But together, so to say, the number of sick days and the number of physician visits provide us with more reliable information, because we have some sort of replication there of scores that is related, that those are at least related to physical health, and they are probably very likely correlated. So there's likely a positive correlation between the indicator of the number of sick days and the indicator that reflects the number of physician visits. And so that covariance or correlation between those two manifest variables, that is what is used in the confirmatory factor analysis model to extract a latent variable, physical health, that accounts for the covariance. So basically that latent variables, you can imagine it to suck up that covariance between the sick days indicator and the physician visits indicator, and then that is what identifies the variance of that physical health factor, so say conceptually speaking. And that's at least roughly that's what's happening mathematically, is that the variance of this physical health factor is based on the covariance between the two indicators. And so then that variance of the physical health factor reflects true score variance that is corrected for measurement error. In addition, there's residual variance in those manifest indicators. That residual variance is reflected by the measurement error variables epsilon 1 and epsilon 2, and so the variances of these error variables is also estimated, and that's the measurement error variance component. The error terms are uncorrelated with the latent factor in the model, so they reflect unique variance that is not true score variance and not explained by the factor. And so then this model allows us to partition the variance into true score variance or factor variance, or we could say common variance that is shared across indicators, and unique variance that is unique to the epsilon measurement error variables. The error variables here are also assumed to be uncorrelated with each other, although this is a constraint that can be relaxed in larger models with more indicators. If there are indicators that share specific variance with one another, then you can allow a correlation between some of those error terms. Now, typically we have more than two indicators in a factor model, because that provides more stable identification of the model and also reduces the likelihood of estimation problems, makes the model more stable. And also we typically have more than one factor, and then when we have more than one factor, we can look at factor correlations. Those would be latent correlations estimated between the factors that are then corrected for measurement error. And so one goal of confirmatory factor analysis is to test measurement models and to look at the reliabilities of the observed variables and look at factor correlations that are corrected for measurement error. More formally, a CFA model could be depicted like this, where we have a factor f1, and the factor f1 is measured by two indicators here, y11 and y21. The first subscript is for the variable, the second subscript here is for the factor. So this would be the first variable measuring factor 1. This would be the second variable measuring factor 1, and we have factor loadings lambda 11 and lambda 21 that are, as we will see, linear regression slope coefficients that have something to do with the relationship between the variables and the factor that they are supposed to measure. And in addition, we have the error variables epsilon 11 and epsilon 21 that characterize random measurement error, as well as variable specific variance that is not shared with the other variable that also is loaded on this factor. And so say epsilon is a blend of error variance and specific variable variance. In terms of equations, we can depict this model by linear regression equations. For the first variable, we would have y11 equals an intercept alpha 11 plus a factor loading or regression slope coefficient lambda 11 times our factor plus a measurement error variable. And the parameters alpha 11 and lambda 11 are constants. They are estimated as part of the model, and then we also estimate the variance of f1 as a random effect and the variances of the epsilon variables also as random effects. We have a similar equation for the second variable with an intercept or additive constant alpha 21 and a multiplicative constant or factor loading lambda 21, as well as the error term at the end. And so in the standardized solution, when all variables are standardized to a variance of 1, the factor loadings have a very straightforward, useful interpretation as correlations between a variable and a factor, as long as each variable has a loading on only one factor. And so then those lambda parameters directly tell us something about the strength of association between the variable and the factor when variable and factor are standardized. But based on the factor loadings and variance components, we can estimate the reliabilities of the indicators. The reliability of the first variable would be given as the unstandardized lambda squared times the variance of the factor, which is estimated as part of the model, divided by the variance of y11, which is also estimated as a model implied variance. The variance of y11 is a function of the factor lambda squared times the factor variance plus the error variance component. And so with this fraction, we can estimate the proportion of variance in y11 that is reliable variance or true score variance. For example, if reliability y11 came out to equal 0.8, this would mean that 80% of the observed variance in y11 is true score variance and only 20% of the variance are error variance. So this reliability coefficient can be interpreted in line with classical test theory. It ranges between 0 and 1, where 0 indicates complete unreliability and 1 indicates perfect reliability. And then for the second variable, we obtain a similar equation but with a different loading squared and a different variance component in the denominator. Now, how do we put this together to a structural equation model or latent path analysis? Let's take a look at that also. We're now combining the idea of path analysis with the idea of confirmatory factor analysis. So we are adding a measurement model to our path analysis to account for error and estimate the path coefficients at the latent level. So we're going to do that shortly, combining path analysis and confirmatory factor analysis, and then we will look at the relationships between the variables at the latent level. That way we can account for measurement error and we can correct the path coefficients for measurement error. In our case, in the example with physical health, functional health, and subjective health, this would look like this. We have now a path model with latent variables. So this looks exactly the same as the manifest path model, except that these variables are now latent variables. We estimate our path coefficients as latent path coefficients. We have latent residual terms, zeta 1 and zeta 2, that characterize residual variance in the latent endogenous or latent dependent variables that is not explained in the model by the other latent variables. And then each of the latent variables is measured by multiple indicators, at least 2. So we have 2 indicators here for physical health, 2 indicators for subjective health, and 2 indicators for functional health, as we did in the confirmatory factor analysis model. And so in this way we can account for measurement error in each of the 3 constructs and estimate the reliabilities of the observed variables, and then estimate the path coefficients at the latent level as well as R-squared values at the latent level, so that we can take measurement error into account. So that's the whole idea of structural equation modeling, is to combine path analysis with confirmatory factor analysis and have a measurement model to filter out measurement error and then look at relationships between variables at the level of latent variables. Now, what are the advantages of structural equation modeling in general? First of all, as we saw, those provide a correction for measurement error, which is useful to obtain unbiased path coefficients, unbiased standard errors, and unbiased test statistics and confidence intervals. We can estimate the reliabilities of the indicators to learn something about the psychometric properties and the precision of measurement. We can test complex causal models. Those are multivariate models, so we can have models with multiple independent variables, multiple dependent variables, multiple mediator variables that are, so say, in between, that are independent and dependent variables at the same time. And we obtain tests of model fit, so we can test our models against the observed data by using a chi-square test of model fit that tells us whether the model implied covariance and mean structure is in line with the observed covariance and mean structure. And so this provides a way of rigorous model testing. We can also conduct statistical model comparisons. If we have multiple competing models, those can be compared with fit indices or fit statistics. For example, when we have nested models, we can use chi-square difference tests, and there are also other fit statistics available for non-nested model comparisons. It's very easy to include missing data in a structural equation modeling analysis by using full information maximum likelihood estimation or multiple imputation. Those are implemented in most software programs for structural equation modeling. You can find videos on missing data handling in Mplus on this channel, where I show how to estimate structural equation models with missing data using FIML, full information maximum likelihood, and multiple imputation. Also, there are various extensions available for structural equation models. They are very flexible models, and I talk about some of the extensions on the next slide. One extension is, for example, for group comparisons, so-called multi-group confirmatory factor analysis or multi-group SEM, where we can first of all test for measurement equivalence across known groups that we want to compare. For example, if we want to conduct cross-cultural comparisons, we can do that with multi-group analysis, or we can compare experimental and control groups with a multi-group analysis, and we can test whether factor loadings, intercepts, error variances are equal across groups. I have several videos and a playlist on multi-group analysis on this channel that you can check out if you want to learn more about multi-group CFA and multi-group structural equation modeling. Furthermore, SEM and CFA are also very, very powerful methods for analyzing longitudinal or repeated measures data when we want to look at variability and change across time. There are many different models available for analyzing longitudinal data, including latent state trait models, latent change score models, latent growth curve models, latent autoregressive models, models for intensive longitudinal data, and you can find many videos on those topics on the QuantFish YouTube channel, for example, about latent change score models, latent growth curve models, latent state trait models. So if you're interested in that, then check out those videos. Furthermore, structural equation modeling and factor analysis can be applied to dyadic data or multi-rater analysis when we have dependencies in the data. So for example, when we're looking at husbands and wives and they're not independent, those scores, or when we have multiple ratings, multiple interchangeable ratings for a target person, for example, multiple customers rating a salesperson, or when we have multiple students rating teaching quality of professors or teachers, then structural equation modeling and factor analysis can also be applied to analyze multi-rater data and to determine convergent validity or rater agreement, while also taking into account measurement error. Furthermore, there are extensions to multi-level structural equation modeling. So when we have nested data, again, we can use structural equation models and factor models at multiple levels, where we have a level 1 model and a level 2 model and factors at various levels. Also, there are mixture distribution extensions of SEM, for example, growth mixture models that allow us to identify previously unknown subgroups or latent classes that differ in their growth trajectories or change trajectories across time. Again, you find some videos on this channel here explaining growth mixture models. There are also some limitations of structural equation models, and so maybe the most important one is that those are not small sample techniques. So if you have only 50 data points or a sample of size 50 cases or 80 cases, then that's probably too small for estimating most structural equation models, because they estimate many parameters typically, and so therefore we need a substantial sample size. And so as a very, very rough rule, we usually use several hundred cases for these types of models. If you really want to know exactly what the minimum required sample size is, typically a good way to find that out is by way of a simulation study. So you can do sample size planning with Monte Carlo simulations. I offer a free workshop on this topic that you can find the link for in the description below for this video, where I show how you can use a Monte Carlo simulation in the Mplus software to determine the appropriate sample size for a path analytic model, and that can be applied to factor analysis and structural equation modeling in the same way. Furthermore, as you saw, when we apply factor analysis and SEM, we need multiple indicators so that we can extract the common variance or true score variance and separate the true score variance from error variance. So we need at least 2 indicators per factor. There are models for single indicator data, however they are more tricky to apply, because then you have to know about the indicator reliabilities ahead of time. And so one advantage of factor analysis is that when you use multiple indicators, you don't have to know anything about the reliabilities ahead of time, but they are estimated as part of the analysis. So you need to have typically at least 2 indicators per factor, and preferably at least 3 indicators for greater stability of the model, and so that may not always be easy to find. Furthermore, since it's a complex multivariate technique with many parameters and with latent variables, there are also more things that can go wrong as compared to conventional correlation and regression analysis and also path analysis with manifest variables, because with latent variables there can be issues of model identification, there can be issues of non-convergence, where a model is too complex or otherwise problematic and will not even converge to a solution, or you might run sometimes into improper solutions where you get negative variance estimates, for example, for residual variances or other variances. And so there are simply more things that are tricky, and it takes more experience to work with these models because they are more complex. You can find some videos on troubleshooting in SEM and convergence issues, improper solutions, also on this channel here. If you're more interested in SEM, check out the description for videos and workshops that I teach for QuantFish. There you find more information. I offer a full course on factor analysis that covers both exploratory and confirmatory factor analysis. In Mplus, I also offer an introductory workshop to structural equation modeling with Mplus, as well as numerous other workshops, for example, on longitudinal SEM using Mplus. I hope you liked this video. If you did, then please hit the like button, subscribe to this channel, leave a comment in the comment section if you like, and I'll see you next time.